Welcome back to OKONKOW Academy. So this is lecture 2, and today we are focusing on functional groups, the reactive portions of organic molecules that determine their chemical behavior. By the end of this lecture, you will be able to identify and name the most important functional group families in organic chemistry. Let's begin with hydrocarbons, compounds that contain only carbon and hydrogen. The first family is alkanes, hydrocarbons with no multiple bonds between carbon atoms. All carbons in an alkane are sp3 hybridized. Examples include pentane, a 5-carbon chain, and cyclohexane, a 6-carbon ring. Alkanes are the simplest organic carbons and are relatively unreactive, which is why they make good fuels. So no multiple bonds is the definition feature of alkenes. The second hydrocarbon family is alkenes, compounds containing at least one carbon-carbon double bond. The double bond makes alkenes significantly more reactive than alkenes because of the exposed pi electrons. Examples include propene, a 3-carbon alkene, and cyclohexene, a 6-membered ring with one double bond. The general suffix for alkene names is "-ene", so as illustrated in the red colored in the red color. Mm. The third hydrocarbon family is alkynes, compounds containing at least one carbon-carbon triple bond. Alkynes are highly reactive. They have 2 pi bonds and 1 sigma bond in the triple bond. The simplest alkyne is ethyne, also called acetylene. That's AC triple bond CH. Yeah. Examples are examples also include one pentyne, as you can see, and two pentyne, distinguished by where the triple bond is located in the chain. So the suffix is "-ine", that's YNE, as illustrated in the red line, in the red colored word. The fourth hydrocarbon family is aromatic compounds. These contain a special type of ring system, most commonly the benzene ring. Benzene has a unique stability due to resonance. We will discuss this fully in a moment. Examples shown here include benzene itself, toluene, benzene with a methyl group, and benzoic acid, benzene with a carboxylic acid group. Aromatic compounds are named using benzene as the parent or as a substituent prefix. So, alkenes. Alkenes are obtained primarily from natural gas and petroleum. Methane, ethane, propane, and butane are all gases at room temperature and atmospheric pressure. Methane is the principal component of natural gas. Higher molecular weight alkanes, pentane and above, are liquids, and very heavy alkanes are solids like wax. The refining of petroleum separates alkenes into fractions by boiling point, producing gasoline, jet fuel, diesel, and other products. So, as an example, that's the structure of methane as we discussed in the previous lecture. Alkenes. Alkenes are enormously important in industry. Ethene or ethylene and propene are among the most produced chemicals in the world. Ethene is the starting material for ethanol. Ethylene oxide as acetaldehyde and the polymer propylethylene, polyethylene, the most common plastic. It also serves as a plant hormone responsible for fruit ripening. So if we date back in biology, senior high school, you could see that ethylene is an agent for fruit ripening. It's a very, very important chemical. Um, the industrial synthesis of these alkenes occur through steam cracking of petroleum. Yes. Propene is similarly important. It is the precursor to acetone, cumene, and polypropylene. But alkenes aren't only industrial. Many occur naturally. Alpha, alpha pinene, sorry, okay, is a component of turpentine. Yes, turpentine, giving pine trees their distinctive smell. There are also alkenes that serves as insect pheromones, like the aphid alarm pheromone shown here. Nature is a rich source of structurally complex alkenes. So yeah, those are the compounds that I've mentioned. These are their structures. These are their structures. So I just wanted to give some applications about them. Alkynes. The simplest alkyne is ethine or acetylene, but alkynes also occur in nature, often with biological activity. Capelin is a naturally occurring alkyne with antifungal properties. Dactylene, found in marine organisms, is an inhibitor of pentobarbital metabolism. These examples show that even the triple bond, often thought of as a synthetic curiosity, appears in nature with real biological functions. So, yes, um, those are the structures and the applications that I've mentioned about them. You can also look into more applications about them. Yeah. Now, let's look more carefully at benzene. All six carbon-carbon bond lengths in benzene are identical, that's 1.36 angstrom. This is intermediate between carbon-carbon single bond at 1.54 angstrom, um, carbon-carbon's double bond at 1.34 angstroms. This tells us that benzene doesn't have alternating single and double bonds. Instead, the pi electrons are delocalized evenly around the ring. This delocalization gives benzene extra stability called aromatic stabilization or resonance energy. So that's what's shown in the red. Uh, So let's look at this diagram here. Benzene is completely planar. All six carbon are sp2 hybridized, and the unhybridized p orbitals on each carbon contribute one electron to the delocalized pi system. So the pi electron density forms two donut-shaped clouds, um, so one above and one below the ring plane. This delocalized pi system is what makes benzene aromatic and confers its unusual stability. So those are the pi clouds. Yes. The lobes of each pi p orbital overlap with the lobes on adjacent carbon atoms. So all six p orbitals overlap continuously around the ring, and the six pi electrons are fully delocalized. Yes, are fully delocalized. Um, that's shared across all six carbons equally. So this is resonance in action. No single Lewis structure accurately represents benzene. The real structure is resonance hybrid of all contributors. This delocalization is the source of benzene's thermodynamic stability. So yes, no single structure is correct. The truth is the average. This is a conceptual breakthrough. Yes. Now we introduce the concept of functional groups in a systematic way, starting with alkyl groups. An alkyl group, uh, an alkyl group is a fragment derived from an alkane by removing um, one hydrogen. Yes. So common examples: methyl, um, that's CH3 dash, ethyl CH3 CH2, propyl CH3 CH2 CH2, and butyl CH3 CH2 CH2 CH2. Yes, so that's the alkyl group. These are abbreviated like Me, Et, Pr, and Bu respectively. Alkyl groups are not functional groups themselves. They are simply the carbon framework that surrounds functional groups. So in the table here, you see their structures, their 3D views. So in analogy, the R is like the body of a car, right? And then the functional group is like the engine that makes it go. Yes, so that's an analogy I can represent. Uh, so yes, the general formula for an alkene is RH, right? It's RH, where R represents an alkyl group, methyl, ethyl, propyl, or any other carbon chain. This R notation is shorthand that allows us to write general reactions applicable to an entire class of compounds. Whenever you see R in an organic structure, it represents any carbon substituent. Yes. So the specific identity of R doesn't change the reaction or at the functional group. Functional group. So yes, R is a placeholder. Focus on the functional group. That's where the chemistry happens. Yes. So phenyl and benzyl groups. Yeah. Two special groups derived from benzene are the phenyl group and the benzyl group. The phenyl group is a benzene ring attached directly to the molecule C6H5, abbreviated PH or AR. The benzyl group is a benzene ring attached via a CH2 group, that's C6H5CH2, abbreviated BN. That's yeah. The distinction matters. Phenyl has the ring directly bonded. Benzyl has a methylene spacer. So you see both frequently when dealing with aromatic compounds. Yes. So that's what they have been illustrated with the diagrams and their abbreviations. Right? Their diagrams and their abbreviations. Uh, yeah. So yeah, those are the diagrams and the abbreviations are here. And then I think there's a symbol to like phi, and then the benzyl to that's it. That's what you can see here. Yes, alkyl halides or haloalkanes. Yeah. So the first heteroatom containing functional group we will study is the alkyl halide or haloalkane. General structure Rx, where X is fluorine, chlorine, bromine, or iodine. Alkyl halides are classified by the substitution of the carbon bearing the halogen. Halogen. Um, yes. So a primary 1 degree carbon is attached to only one other carbon. A secondary, that's 2 degree carbon, is attached to other carbons. A tertiary carbon is attached to three other carbons. This classification directly affects reactivity in substitution and elimination reaction, which we will cover in detail in upcoming lectures. So yeah, so we can preview SN1, SN2, E1, E2 reaction briefly. This is foundational for those mechanisms. Now, let's talk about alcohols. Alcohols have the general structure ROH, a hydroxyl group attached to an alkyl group, like alkyl halides, right? So, um, alcohols are classified as primary, secondary, uh, or tertiary based on the substitution of the carbon bearing the OH group. A special case is the phenol, right? Where OH is attached directly to an aromatic ring. Phenols are significantly more acidic than regular alcohol due to resonance stabilization of the phenoxide anion, which we can look into that. Methanol and ethanol are the simplest alcohols. So these are some of the structures of alcohol, right? So the one we, as I've said earlier, is the primary, 2 degree, secondary, 3 degree, tertiary. So those are the examples. Right? Alcohols can be viewed in two ways: as hydroxyl derivatives of alkenes or as alkyl derivatives of water. This second perspective is very useful. Right? So water has OH bonds with a bond angle of 104.5 degrees. An alcohol replaces one hydrogen of water with an alkyl group, giving a similar geometry. So yes, oxygen in both water and alcohol is sp3 hybridized with two lone pairs. This structural similarity explains why alcohols like water can act as both weak acids or weak bases, like bases. So those are the structures. The structure, right? The structure. Then the angle to is shown here. Ethers have the general structure. RO al, an oxygen atom bonded to two alkyl groups. The bond angle at oxygen is approximately 100, right? 100 degrees, slightly compressed from tetrahedral due to lone pair repulsion. Ethers can be as acyclic, like diethyl, the classic laboratory solvent, or cyclic, like tetrahydrofuran, another common solvent. You can look into those examples, right? You can look into those examples. Ethers Ethers are relatively unreactive under normal conditions, making them excellent solvents, but they can react with strong Lewis acid and they form dangerous peroxides on prolonged exposure to air. Yes. Now let's talk about amines. Amines are nitrogen containing functional groups. General structure RNH2. Like alcohols and alkyl halide, amines are classified as primary, secondary, or tertiary. Yes, so they also have such classification. A primary amine has one alkyl group on nitrogen. A secondary amine has two. A tertiary has three. Has three. Yes. Amines are Lewis bases. So the nitrogen lone pairs is available to donate to acid. Cyclic amines like pyrrolidine, that's pyrrolidine, and aromatic amines like aniline are also important structural types. Yeah. So yes, you should also know that tertiary amine means three groups on N nitrogen, not three carbons away from nitrogen. So that can be a confusion. So you have to take note of that. You have to take note of that. Aldehyde and ketones. Yeah. So these are their structures, some of them. Right? So both aldehyde and ketones contain the carbonyl group, a carbon double bond to oxygen. In an aldehyde, the carbonyl carbon is bonded to at least one hydrogen. So general structure is RCHO. So R dash CHO. In a ketone, the carbonyl carbon is bonded to two uh, carbon groups, right? Carbon groups. And the general formula structure, the structure is R dash CO dash. So both are extremely important in biological chemistry. Example include sugar, amino acids, and many metabolic intermediates contain carbonyl group. So you can look into that. Like you can do further research on this. You appreciate them. So yeah. So you have to also know that the carbonyl carbon in both aldehyde and ketone is sp2 hybridized and adapt a tribunal planar geometry. Bond angles around the carbonyl groups are approximately 120 degrees. But here, because of the oxygen influence, you could see that it has tilted, like it has deviated from some of the angles. So here you can have uh, 121, 121, 108. Yes. Mm. This geometry has major consequences for reactivity. Nucleophiles attack the carbonyl carbon from above or below the plane, approaching at approximately 107 degrees. So that's the Bergy-Junus angle. Yeah, you can search more on that. This special requirement explains the stereochemical outcomes of many addition reactions. So we can look more into Bergy Junus angle for advanced students. Yes, so it shows more depth into this knowledge. Carboxylic acid, esters, and amides. Amides, yeah. So basically, this slide shows a family of carbonyl containing functional groups, all related to the carboxylic acid. A carboxylic acid has the structure R-COOH. Replace the OH with OR and you get an ester. Yes, get an ester. Replace it with NaNO2 and you get an amide. You get an amide. Amide. Uh, Two acyl groups connected through oxygen give an acid anhydride. So replace OH with Cl and you get an acid chloride, the most reactive of all. These compounds are all interconvertible and they represent some of the most important reactions in organic synthesis, nucleophilic acylic substitution. So yeah, so that's it. That's for carboxylic. When you replace the OH with OR, you get what ester. That's shown here, right? You replace the OR with what Cl, you can get what acid chloride, and then when you replace the OH again with what NR2, you get amide, and then replacing the OH with what OOR, that give you acid anhydride. Yes, acid anhydride. Nitriles. So nitriles have the general structure of C triple bond N, a carbon triply bonded to nitrogen. The carbon is sp hybridized, making nitriles linear at the CN triple bond. Yeah. Examples include acetonitrile, the simplest nitrile and a common laboratory solvent. Um, yes, common laboratory solvent. And yeah, used to make as acrylic fibers and benzonitrile. Benzonitrile. Yes, benzonitrile. So those are the other names that you can call them. Yeah, you have ethene nitrile, propene nitrile, and benzene carbonitrile. Yeah, used to make, yeah. So nitriles are important synthetic intermediate because the C triple bond N group can be hydrolyzed to a carboxylic acid or reduced to an amine. Yes. So yes, let's look at this summary. So summary of important families of organic compounds. Yes. So this summary table collects all the functional group families we've discussed into one reference sheet. So take a photo, you can take a photo of this slides or copy it into your notes. This is your master reference for the course. Each family is defined by its characteristic functional group, and you should be able to identify any of these by sight. More importantly, you should know the general reactivity associated with each. Alkyl halides undergo substitution and elimination. Yes, you need to know that. Um, Alcohols can be oxidized or act as nucleophiles. Carbonyl compounds undergo addition or act as ester substitution and so on. Yes, so you need to note that. To know that. So this is the continuation of the table, the summary of the organic compound, the functional groups. So you can take note of this one too. You can take note of this one too. So yes, that brings us to the end of lecture 2 on functional groups. So we've covered the full landscape of the most important organic compound families. hydrocarbons, alkenes, alkenes, alkynes, and aromatics, as well as heteroatom containing families including alkyl halides, alcohols, ethers, alkyl halide, amines, aldehydes, ketones, carboxylic acids, and their derivatives and nitriles. In the next lecture, we will begin exploring the reactivity of these groups in earnest. Well done today. Review these structures and make sure you can draw and name each functional group from memory. Um, Thank you for today and see you in the next lecture. Bye for now.